Welcome everyone to today's session. So we're very excited to have you all join us for our second webinar of the series. I'll hand over to John from here, who's going to be chairing for us today. So to you, John.
Okay, thanks very much. Well, we've got a very packed schedule. We've got an hour of presentations and then a break, and then a part of an hour of discussions. So I'm going to go fairly quickly through the presentations now. It's being recorded, so you can go back and see them again later. The discussion won't be recorded. If you've got any questions, put them in the chat, or if you want to have a chat in the chat and sort of keep the discussions going. We'll pick it all up and enjoy getting into it in more depth in the second hour. So without more ado, Christian Bauer from the Scherrer Institute. Just say briefly, Christian's been quite active looking at realistic life cycle analyses for hydrogen in response to the sort of debate that was started in, I guess, August this year, saying how bad hydrogen could be, and I think Christian will present us with a more balanced. Okay, Christian, please, the floor is yours.
Yes, good afternoon, everybody. Let me share my screen. Yes, thanks for giving me the opportunity to talk about this work. I think it's important, and it has been discussed widely during the last month. So, as John said, I will try to give a more balanced perspective on the greenhouse gas emissions associated with this hydrogen production. And yes, as you all know, there are a lot of different pathways to generate the hydrogen. And they are often associated some colors with it, like starting from the bottom, the brownish stuff, core gasification, then natural gas reforming, pyrolysis, then one can convert biomass to hydrogen, and finally one can convert renewable electricity or also nuclear electricity to hydrogen. And those different pathways are very different in terms of their greenhouse gas emissions. And actually, the goal is now to identify those which are clean in terms of impacts on climate change, and differentiate from those which are not clean in terms of impacts on climate change, and also to identify basically the boundary conditions under which certain pathways can be considered as a low carbon production pathway, and the boundary conditions under which this is not possible. And in my talk now, in the 15 minutes I have, I will focus on those pathways, basically electrolysis using renewable power, or also some current power generation mixes, a few words about biomass conversion, and then more on the natural gas conversion pathways with and without CCS, because basically in the public discussion, it's often a kind of competition between the green hydrogen using electrolysis and renewable power, and the blue hydrogen with natural gas conversion with CCS. And I think that's not always very productive. And I think I can provide some facts for decision making also. And that's the goal of this talk today. So what do we have to do when we want to quantify the greenhouse gas emissions of hydrogen production? Well, basically, we have to perform something which is called life cycle assessment. And the key aspect of life cycle assessment as such is that it quantifies the environmental burdens along the whole life cycle, as the term says, of a product, of a service. And that means that all material and energy flows along the life cycle from the production of a good or service, its use and its end of life are taken into account. And with such a comprehensive perspective, one can basically compare different products and services in a balanced way, and quantify not only greenhouse gas emissions but also other environmental burdens. But for the sake of this talk, I'm focusing on greenhouse gas emissions. Now, if you think about this concept a bit more, then you realize quickly that in the end, a complex exercise. Just think about washing your clothes. That needs a washing machine which needs to be produced and operated, and then probably recycled at the end of its life. Operation of the washing machine needs electricity for example, from a wind turbine. This needs to be produced, operated, and then recycled at the end of its life. All the components of both the wind turbine and the washing machine, they need transport activities, and also the lorries have to be produced, operated, and disposed of. And maybe in all this is some web service included. That's why you need some internet, and also that has to be taken into account. And in the end, it turns out that life cycle assessment basically always tries to represent the whole economy in a way, because all those processes are interconnected. And of course, in the life cycle of hydrogen production, not everything is equally important. And I will show you the most important elements in a minute. But now back from the washing of clothes to the focus of my talk. Basically what I want to present is a comparison in the end of greenhouse gas emissions associated with hydrogen from electrolysis, with the greenhouse gas emissions associated with natural gas reforming, with and without CO2 storage, and a few words about the biomass conversion pathways as well. But in the context of biomass conversion, one always has to take into account that the resources, the sustainable biomass resources, are very limited, and there's also competition for other uses. So in the end, if we think about large-scale hydrogen economies, I think only these two pathways are realistically able to provide or to supply large amounts of hydrogen, which might be used in the future. So key parameters in the life cycle of hydrogen production, either from electrolysis or from natural gas reforming. Well, for electrolysis, it's actually pretty simple, because the most important factor is the greenhouse gas intensity of the electricity consumed, and so let's say fixed contribution from the infrastructure construction, like the electrolyzer, is relatively minor in terms of impacts on climate change. That's why it's really, if one knows the electricity source used for electrolysis, then it's basically already answering the question whether the hydrogen produced from it is carbon low in terms of carbon emissions or not. Of course, if we think about electrolysis directly coupled with renewable electricity generation, then today at least it's not really profitable or in any way economic, and that's why often this electricity from the renewables is supplemented with some electricity from the grid, and that also has to be taken into account in the overall carbon balance. Hydrogen from natural gas with CO2 capture and storage is a bit more complex in its life cycle assessment, because there are basically two, or one can also say three, key elements in that. One is the CO2 removal rate at the hydrogen production unit, with different options there in terms of technology and CO2 capture rates. And the second very important factor here is the methane emission rate along the natural gas supply chain. And since methane is a very potent greenhouse gas, already small amounts of natural gas leaks and emissions along the supply chain, they do have a considerable impact on the overall life cycle performance of this hydrogen production pathway, and that's what we will see in a minute. And then this third point here in brackets, if there are substantial methane emissions along the natural gas supply chain, then also the time horizon for the global warming potentials becomes important, because if we compare the 20-year time horizon to the usually used 100-year time horizon for quantifying global warming potentials, then we realize that there's a factor of 3 in the impact of methane, about a factor of 3, and that's why these methane emissions along the natural gas supply chain, they become much more relevant if we look at shorter time horizons. So that's what I've mentioned already before. Electricity production related greenhouse gas emissions are the key factor for electrolysis. And what you see here, I guess most of you are familiar with that, that coal power has the highest life-cycle greenhouse gas emissions per kilowatt hour of electricity, followed by natural gas, and with some margin then at the lower end, all the renewables and nuclear power. So it's basically showing that if we operate electrolyzers with this kind of electricity, then the hydrogen can be considered as low carbon fuel or feedstock, and that will become clear in the next graphs. This shows you here then the methane emissions from the natural gas supply chain, which I've been talking about before. That shows here on the left axis greenhouse gas emissions per cubic meter of natural gas. And here you have different origins, basically producing countries with import to Europe or Germany. And on the right-hand side, you have the methane emission rate in percent methane emissions per natural gas supplied. And you can see here a very considerable variation. For example, if the natural gas is coming from Norway, then those emissions are really, really low. But if it's coming from countries like in the north of Africa, then they can be really, really high. And that makes a very important difference then in the life cycle emissions of the hydrogen produced. So, and that's what you can see here basically. That's a bit a complex graph, and I will walk you through. On the left-hand side, you see here the life cycle greenhouse gas emissions in terms of CO2 equivalents per megajoule of hydrogen, and translated into kilogram per kilogram of hydrogen. And here you see 3 different cases for the methane emission rate. So we picked 0.2%, 1.5%, and 8%. So the 8% was this dysfunctional natural gas infrastructure. The 1.5% corresponds about to the current European supply mix, which has substantial shares of imported gas from Russia, and that's why emissions are not close to zero here. And that would, for example, be, well, I think that's the goal of the natural gas extraction association or something like that. So Norway, the Netherlands, UK would be in this order of methane emission rate. And then we have here a case of gray hydrogen production, so just SMR without CO2 capture. Then we have a blue hydrogen case with low capture rate or low CO2 removal rate. And then we have a blue hydrogen production case with a high CO2 removal rate. And you can see that both the methane emission rate here and the difference between low capture rate and high CO2 removal rate makes a big difference in terms of life cycle greenhouse gas emissions of hydrogen production. Because if we compare the gray hydrogen with this best case here, then we get a reduction of about, let's say, 80% in terms of greenhouse gas emissions. But if we look at the low capture case, then we only get about 50% reduction. And this reduction gets smaller and smaller the higher the methane emission rate of the natural gas supply chain gets. And this is actually what you can see here in this graph, but this is too complex, so I took it apart. So what you can see here is global warming potentials for a time frame of 100 years in terms of gram CO2 equivalent per megajoule of hydrogen, or natural gas combusted. So that includes the combustion emissions of the natural gas and the natural gas supply as a function of this methane emission rate of the natural gas supply chain. And you can see here that those 4 lines, they present the gray hydrogen, so the natural gas reforming without CCS. Then the 2 blue lines are the 2 cases with carbon capture and storage I've mentioned before. One, the case with a low CO2 capture rate, the other one with a high greenhouse CO2 removal rate, and in between the line for the natural gas combustion, including natural gas supply. And here this green area basically represents the potential greenhouse gas emissions of water electrolysis using renewable power. Why this large or relatively large bandwidth? Because if you have, for example, hydropower to supply the electricity for the electrolyzer, then you are at the bottom here of this range. And if you use PV electricity at a non-ideal site with not so much irradiation, then you would be at the top of this bandwidth. And you can see here that the blue hydrogen, the best case option here in our assessment, comes close or gets comparable with green hydrogen production below about 1% of methane emission rate for the natural gas supply chain. And I think that's an important lesson to learn. And it's also important that what you can see here, those two markers, they represent electrolysis using European average supply or US average supply today. And those emissions are substantially higher. So as soon as some shares of grid electricity, average grid electricity, are included in the electrolysis, then that has a substantial increase in terms of greenhouse gas emissions as an effect. And now I mentioned before the time horizon for the global warming potentials. What you see here is 100-year time frame, 100 years time frame. And what you can see here now is the 20 years time frame. I don't want to get into details, but if I switch back and forth, you simply see that for the 20-year time frame, as I've said before, this methane emission rate along the supply chain gets much more important because of this comparatively higher global warming potential of methane with a shorter time horizon. At the beginning, I also said I would show some biomass results, and I tried to visualize that with this graph. Same lines as you've seen on the two slides before, and now here the ranges of biomass conversion for hydrogen production without CCS and with CCS. And that's only the case if residues from agriculture or sustainably harvested wood are used, so no dedicated plants, which might come along with land use effects, which are difficult to assess. So those cases are not included in this graph, but it basically shows that if one uses such kind of biomass with CCS, then one can generate negative emissions by removing CO2 from the atmosphere. I think even if this kind of biomass is a limited resource, it's still an important lesson to learn. So with this, I think I'm in any case running out of time, so I will finalize with some key messages and some comments in the larger context, which might be important in the big picture, so to say. And what I was trying to show and hopefully showed is that blue hydrogen definitely can qualify as a low carbon energy carrier or feedstock under the condition that the methane emissions along the supply chain are minimized, optimally below 1%, or the lower the better, of course. And then we need at least 90% CO2 removal rate at the hydrogen production, and I think this is feasible with current technology. But there's a but. I mean, these conditions, they have to be ensured by proper regulation and certification. And I think that's really important because if I may say so from a personal perspective, in any kind of industry which wants to go green or climate friendly or low carbon, whatever, we see that some greenwashing activities are taking place. And I think we really have to make sure that this doesn't have a negative effect here on the true quotation marks climate balance and climate impacts of hydrogen, because really if we're talking about hydrogen economy on large scale, then we really have to make sure that the hydrogen used there is climate friendly. Otherwise it doesn't make sense to use it as a measure against increasing temperatures. And then I think both yeah, since both blue and green hydrogen qualify as low carbon energy carriers, I think they can and should play important roles. To which extent they will develop, I think that depends a lot on costs and CO2 pricing, and also availability of the industry in terms of scaling up their production. And finally, I think, just as a concluding remark, hydrogen needs to be supplied in large quantities for achieving these net zero goals. And the most promising, at least from my perspective, use sectors will definitely be industry and aviation, maybe also shipping and long distance road transport. With that, I am done. And if anybody is interested, you will find here my contact details, and I'm available for the further discussion, of course. Thanks.
That's great. Thanks very much, Christian. And I mean, we had a question in the chat. The presentations will be on the website as well as the recording. So you can go back and get the details. So our next speaker, Sean McCoy from University of Calgary. Very, very grateful that Sean has managed to get up early to join us. It's really appreciated. So Sean's from the Department of Chemical and Petroleum Engineering and the Global Research Initiative on Sustainable Unconventional Resources. I don't know whether hydrogen from fossil fuels included in unconventional resources, but perhaps you'll explain to us. So over to you, Sean.
Okay, great. John, thank you very much for the intro. Can you see clearly my slides?
Yep, looks good.
Excellent. Yeah, so interestingly, unconventional resources in Alberta is basically a special term for oil sands or unconventional gas, really. But yeah, certainly, I think it's broadening. My work wouldn't fit into either of the bins on oil sands generally, or hydraulic fracturing or something like that. So I do tend to focus on things, as some of you might know, typically on CCS and how CCS plays a role in delivering a net zero future, really. And that's what I'm most interested in. And so I think this, I really appreciate the opportunity to come today. John asked me to give you a perspective on the hydrogen landscape in Canada, and particularly what's happening in Alberta, because that's what I can speak most clearly to. And it's great. It's like I knew exactly what Christian was going to say in his presentation. So it actually turns out, I think some of his messages are reflected in what I have to say toward the end in mine. So with that, I'll get started. And what I'm going to do is get going on a review to start with of the broader Canadian picture, and then I'll dive into the specific Alberta picture. So with that, let's get started. So the Canadian federal government back in, I guess it was late 2020, released a national hydrogen strategy. And so at the time, so to be clear, that Natural Resources Canada released this strategy, and Natural Resources Canada would be sort of like an energy ministry, but because it's federal and energy resources are controlled provincially, it has sort of a more of a little bit like Department of Energy in the United States, sort of a guiding role. It doesn't kind of directly dictate what gets done at the provincial level, but it sort of has this broad national strategic role. And that's what it's doing here. So they developed this framework at the time when our national emissions reduction target was 30% below 2005 by 2030 and net zero in 2050. But just in the run up to the election we had this year, the party in power, the Liberal Party, increased the ambition for our 2005 target to 40 to 45% below in 2030 and continue with the target of net zero in 2050. And somewhat like in the UK, we enshrined those targets in what's termed the Canadian Net Zero Emissions Accountability Act. So they're legally binding now, although many argue that the binding part isn't that strong. There's not that many teeth in this law, but anyway, it's now in a law. And the way the federal government's primarily doing this is kind of both with pricing and with some specific regulations. So they're doing things like right now introducing a clean fuel standard, which is sort of like a life cycle standard on fuel carbon intensity. It's going to be focused for the most part on liquid fuels, as far as I understand, but it will sort of look like, for those of you who might be familiar with like the California Low Carbon Fuel Standard, it'll look a little bit like that. And I'm not sure where hydrogen sits in there. It certainly would be involved for transport, but probably not as a stationary fuel. But in any case, the other part of this is setting up a carbon price backstop. And so the federal government basically says to the provinces that you must have an equivalent pricing system, or something which gets you to an equivalent shadow price, more or less. And that shadow price or direct price has to get to $170 a ton on the majority of your emissions by 2030. At least that's the federal government target at the moment. So once this was announced and the election happened, interestingly enough, a lot of companies all of a sudden who had been relatively quiet sat up, and I think there's a lot of attention, and that's really being enforced by the steady drip of announcements out of COP. So what does the roadmap say about our targets for hydrogen specifically? They specify that we want to get to 4 million tons of hydrogen per year produced and used in Canada by 2030, growing to 20 million tons a year in 2050. I believe these targets are predominantly for domestic use. This does not pertain to sort of export markets, although that's clearly on the minds of the government, both provincially and federally. And this would be about 30% of total final energy demand in Canada in 2050, and hopefully avoid about 190 million tons CO2 equivalent per year. And for reference, so our 2005 level of emissions is something like 730 million tons of CO2 equivalent. So it would be a pretty decent share of an emissions reduction, depending how you want to count that against a business usual or a 2005 number. They then make recommendations, a total of 32 of them, and they are spread across 8 pillars. They include strategic partnerships, de-risking investments, innovation, codes and standards, enabling policy and regulation, awareness, regional blueprints, international markets. And I think the most important thing, personally, for the Canadian situation is this idea of regional blueprints, which I think you could translate to hubs, thinking about development of hydrogen hubs in Canada. So let's take a quick look at where across Canada things are looking with respect to those sorts of hubs. So in Canada, here we are going from west here in British Columbia all the way across to the east. Basically, for those of you who have been or know a bit about Canada, you know that we have very diverse resources. For example, Quebec, Labrador and Newfoundland, in fact, as well, but Quebec and Manitoba, and to a certain extent Ontario, these grids tend to be generally low carbon intensity already today, with large hydroelectric resources. If you took the average across Quebec, Ontario, and Manitoba, it would be probably close to zero in terms of operational emissions. Then you have to add in properly hydrogen across the life cycle emissions from, for example, hydro reservoirs in Quebec, and fuel chains and things like that. Nuclear, there's a lot of nuclear in Ontario. So this would be very low, nonetheless, low emission electricity. If you looked at Christian's graph, it would be grid intensity that is quite low, getting towards where you have this sort of green hydrogen number start appearing in his plots. And if we look over to Alberta and Saskatchewan, on the other hand, we see a much higher CO2 grid today with strong use of coal, particularly in Saskatchewan. Many of you know that's where the Boundary Dam CCS project is. Unfortunately, they've only done that on one plant, and they have many other coal plants that are unabated. There is a plan to phase out coal across Canada. Alberta is well on its way to doing that. Saskatchewan is less excited about that plan. But right now, the grids are very high CO2 today. The flip side is that we have very large natural gas resources in Alberta, northern British Columbia, and into Saskatchewan, and very large CO2 storage resources, which I'll say more about. And in fact, in Alberta, I'd say these are no longer just resources, they're actually becoming reserves. And if we look over to British Columbia, we have a relatively low carbon dioxide grid. Again, this is an interesting place. Lots of hydro, quite a bit of gas isolated up in the northern corner of the province, and along with CO2 storage capacity up here. But that gas is a long way from the demand centers of Victoria and Vancouver, or even Edmonton here in Calgary. So the distances mean to me that unless we develop a national sort of backbone, as we have with gas pipelines, we could very well have a very regionalized developments of hydrogen. And where are the markets going? Well, as an example, in Varennes, Quebec, the Hydro-Quebec, based on its low grid intensity, is building an 88 megawatt electrolyzer. So very big electrolyzer. I don't know where that sits in sort of global ranking of electrolyzers today, but that electrolyzer, interestingly, will provide hydrogen for green fuel production. So biofuels, basically, from, I believe it would be from forestry residue and landfill materials. So very interesting use there. Then if we were to look over in Ontario, we're seeing electrolyzers being put in for grid blending of hydrogen to natural gas system. And if we went over to Alberta, here we're seeing use of hydrogen being contemplated in heavy duty truck fleets. I mean, I think that's happening elsewhere in the country, but we have a pilot project where we're running trucks between Calgary and Edmonton and along some other major freight corridors in the province, and as well as building some hydrogen fueling infrastructure there. So again, what is playing out, where that hydrogen would be used is very different. And what we've also seen is a lot of interest in southwestern Ontario, particularly around the area of Hamilton. We have quite a bit of heavy industry in that area. And there's been interest in talking about using hydrogen for steel making, for direct reduced iron steel making. So lots of different things happening, lots of different clusters, probably different resources that will develop in different parts of the country. And so let's jump into taking a look at the Alberta situation now. So the existing hydrogen market in Alberta is enormous. So right now, we have something like 5,400 tons a day of hydrogen that we're producing. That's primarily from natural gas. Now, this is not hydrogen for mobility. This is not hydrogen as an energy vector. It's hydrogen as a feedstock for heavy oil upgrading and refining typically. But we also use a bit for maybe 10 or 20% for fertilizers and methanol production. The current demand is anchored near Edmonton, so in the center of the province of Alberta, and also north in Fort McMurray, where that is almost all being used for oil and gas for upgrading and refining. And so let me just zoom in on what the Edmonton region looks like here. So this is sort of the Edmonton's up here, and what I'm showing you is a map that expands out here of the sort of Edmonton region and the interesting features there that relate to hydrogen and also to carbon capture and storage potentially. So right now in this box called, I guess, the Alberta Industrial Heartland, seems to be the name that's emerged over the past few years for this. There's about 2,000 tons a day of hydrogen being produced there, and we already have production of blue hydrogen happening. Now, this blue hydrogen would be what Christian referred to as sort of a low capture rate. This is from the Shell Quest project, which is at the Scotford Upgrader. The carbon dioxide for that project is fed into the pipeline operated by Shell, and it runs away from the upgrader north, sort of as the crow flies, about 100 kilometers. As the crow flies, or not less than that, maybe 50, but up to an injection site here. That injection site is doing very well. In fact, I think some of us speculate that there's lots more capacity in that site than Shell would be using currently with the CO2 from Quest. Then there's another location, which is the Northwest Redwater Upgrader, where they're actually capturing CO2 off shifted syngas, where they gasify bottoms from the refinery to produce hydrogen that they need for upgrading. They capture CO2 there, and that CO2 goes into a different pipeline. And that pipeline is taking the carbon dioxide well south, sort of several hundred kilometers, down to an EOR project down here called Clive, operated by Enhance Energy. There's potential to, that project I think is public, that it's really designed to take the CO2 that's already being produced by Northwest Redwater, and another facility which is called Nutrient Fertilizer. I didn't include that in some of the totals I've been doing, depends who you talk to. For example, this map includes the Nutrient facility in its total. It's making hydrogen for fertilizer, so that's an air-blown SMR, and then Haber-Bosch. So that CO2 all goes down this pipeline to an EOR site. But the point here is that we have infrastructure being developed that can move hydrogen around, and it can also, a lot of production that's happening, and for storage as well. So this is a very interesting region, and in fact, this has become a region which has become an official hydrogen hub in sort of the federal kind of strategy. And so there's a group that's now trying to develop projects and uses for hydrogen in this space. And I'll talk more about those in a minute. So what would the potential demand? I've talked about there being 5,400 tons a day of hydrogen being produced in Alberta. What would the potential demand look like? So based on some studies that have been done in the Alberta Industrial Heartland by a group called the Transition Accelerator, which has been specifically formed to do this work. I was an advisor to this one. We guessed that there was about 1,300 tons a day of existing gray hydrogen, 600 tons a day of hydrogen that could be used to displace diesel use, and potentially some gasoline in heavy duty vehicle fleets in the Edmonton region. And we looked at this from a number of different angles, so this is a pretty robust number. And potentially 1,500 tons a day for space heating. Now, whether that makes sense, I think, is a really interesting and open question. And it's highly variable, because in the summer we don't have much demand. In the winter, we have lots. When it's minus 40, the challenge is a heat pump looks a lot like a resistance heater. So there may be a case for some hydrogen in the gas grid here. And in fact, there's some projects looking at doing that injection. If we went up to Fort McMurray, based on some numbers that a grad student of mine has run, there'd be something like 2,000 tons a day of existing gray hydrogen that could be switched to blue. Hundreds of tons a day of hydrogen could be used to displace diesel. And it's actually not diesel, it's a distillate fuel that you couldn't put in your car and call it diesel, but it's a distillate fuel used for oil sands mine trucks. So these are the enormous dump trucks that are moving around bitumen. And well, actually they're moving around the sand containing the oil. And then there's almost 15,000 tons a day of hydrogen that could be generated to displace natural gas for oil sands process heat. So for decarbonization, basically pre-combustion, distributed pre-combustion capture system. Whether that makes sense is a really interesting question. The companies and consortiums are actively looking at that now, and sort of it's competition between CCS and hydrogen, CCS on the sites or hydrogen being moved to those sites. And we've actually done some work, and I was on that, and I've been pretty surprised that unfortunately the cost of getting hydrogen all the way up there, or building hydrogen production all the way up there, makes it a little more expensive than you might think. But of course, there's an unknown export potential of hydrogen, ammonia, synthetic fuels, and so many caveats here, of course. But if I added this all up, this would be about 3,500 tons a day in the Alberta Industrial Heartland, or 1 million tons a year of hydrogen. And if Fort McMurray could be like 6 million tons a year if you really thought about using it for fuel gas. So these are huge chunks in that 20 million tons in 2030 number. And we're actually taking steps to doing that now. So there have been multiple projects here announced in Alberta. This isn't an exhaustive list, but I think I've captured all the big ones. Right now, we have projects being proposed, 4 of them that are really notable, that range in capacity from 1,500 tons a day at the large end down to maybe 500 tons a day. And these are estimates. Some of the projects are quoting per year. This Shell Polaris project doesn't actually tell you how much hydrogen they're making. They just tell you how much CO2 they're going to catch, interestingly. And they range in where they're going to be going, from refining. You see a lot of these going into refining. So these will be replacing that 1,300 tons a day of gray hydrogen that's currently used. Some being talked about injection into the gas grid. And this Air Products plant's talking about having liquid hydrogen for vehicle fleets, a small amount that would be directed there, and presumably the rest into other sort of merchant uses. And there is one project by Mitsubishi and Shell that's been proposed. It's not really clear where it sits, but it was a very recent announcement where they want to move the hydrogen to export markets as ammonia. So very interesting emerging slate of projects here. If you added all this up, this is something like 3,000 tons a day of hydrogen, I would guess, including the unknown from Shell. And this would be, so this approaches like the total demand right here in these projects that we estimated for the Alberta Industrial Heartland, which is quite interesting. These projects, if you added up this capacity, need about 10 million tons a year of storage. So the question is, do you have that? And the good news is probably. So Western Canada has been the site of study after study on storage. If anyone of you works in storage, you know that Stéphane Batchou has studied the Alberta Western Canadian Sedimentary Basin extensively. And so there is a lot of capacity if you add up the western, so the basin that extends from northern British Columbia through to southern Saskatchewan, you'd see, and into the US, but in that Canadian section, you'd see something like 300 gigatons of potential capacity. Of course, that's potential. It's a resource, not a reserve. And so additional work is needed to get there. The positive news is that we are doing that work now. We probably have tens of millions of tons a year of study, of work that's been done to demonstrate real injectivity. We have a law that governs access to the subsurface. That's been clear for many years. We have a system for post-closure stewardship or post-closure liability management, and the regulator has the tools. The challenge, however, is that recent government moves have created some uncertainty here. They've announced a new process to access the pore space. And what you've seen is there are a whole bunch of hydrogen announcements and everything's gone on hold while the government goes through sort of a request for information and a request for proposal process, because in a nutshell, they're trying to force creation of hubs by the way they allocate the rights to storage in the subsurface. So they're not doing a call saying build a hub, we'll support you. They're saying, tell us you're going to build a hub, and if you are, we'll give you access to the pore space storage rights. So it's interesting to see how that's all going to work out. Very different than things have been done here before or anywhere else in the world, I think, at this point in time. So we shall see. So I guess let me end up here. I'm probably a little over time. Let me end up with some thoughts on where Alberta goes from here. And I think this ties a little bit back into what we just saw from Christian. So first, I think we need to acknowledge that hydrogen here in the provinces is a response to climate change, and we don't need to kid ourselves about that. This is a very climate, and our response to it's a very difficult conversation here in this province. And we really need to be therefore thinking about the whole cradle to gate, particularly on our upstream gas. While I think Alberta has done a pretty good job of managing upstream gas, at least in terms of its regulations, that is the methane emissions that Christian was talking about, we need more measurement to really verify this and be able to demonstrate it to the world and sell a truly low carbon hydrogen if we're going to do it globally and make sure we're meeting our commitments domestically. The second is that we need to really continue pushing development hubs and start figuring out where the markets make sense and are economically viable and what's going to take to develop them. Right now, it is really hard to see how, for example, that Air Products reformer at 1,500 tons a day, where that hydrogen goes. Certainly can go to some of the gray, replacing gray hydrogen, but that gray hydrogen is already being supplied. So it's sort of, I think, additional. And the question is, where's that additional hydrogen going? What makes sense? How do we get it? How do we get the markets developed? We certainly need more investment in CO2 storage. I think anyone in CCS community would probably say that's of course. And we do need to understand that green hydrogen is going to become economically competitive and maybe preferred. So we really need to accelerate our push to getting to demonstrate that we have low carbon hydrogen and be thinking about the timeframes and path forward that are involved. And know that the government does have a role to play here. I think that's the government is stepping up, and in fact, on this last bullet, the provincial government will maybe this week, perhaps next week, be announcing its provincial hydrogen strategy. So that's apparently with the cabinet for approval. So we should be seeing that coming out soon. Keep your eye on this space. And with that, I'll wrap up, and I hope I'll have time to have questions at the end. So thank you.
Yep, there'll be plenty of time for questions in the second half. Thanks very much, Sean. So without more ado, because we're running a bit over time, but never mind. Stephen Florence from AECOM will come and talk about hydrogen production from biomass with CCS mostly, I guess. So over to you, Stephen.
Thank you, John. I'll just try and share my presentation. Okay, so thanks very much. My name is Stephen Florence. I'm a senior engineer at AECOM in the energy transition team. And I'm going to talk to you a little bit on hydrogen from biomass and a study we did to do with advanced gasification for the UK government. So I'm going to run through a bit about the study, give a sort of process overview of the Biomaster hydrogen, and go through some of the opportunities and barriers for these technologies, and give you some of the conclusions. So the study itself was called Advanced Gasification Technologies, looking at converting biomass and municipal solid waste to a range of fuel products, including hydrogen, but also methane, methanol, and FT fuels. The study also encompassed the current status of the AGT technologies, as well as looking at the next generation of technologies being developed. Then the later part of the study performed some techno-economic analysis of various options for the technology for each of the different fuels. And there was a particular focus on looking at the opportunities and the barriers to bringing these technologies into fruition, essentially. And this work was conducted with Fichtner Consulting Engineers as well, and was performed for the UK Department of Business, Energy and Industrial Strategy. And you can find the study at the links here, or just put BEIS Advanced Gasification Technologies into your Google search and you should find it. And as has been mentioned, the presentations will be shared, so you should be able to access that. So some of the key messages coming out of our study was that the CO2 balance should be studied further. There's a lot of potential in this area, and we'll touch on that later in the presentation. A realistic approach to feedstock availability and utilization is required. We don't want to be taking biomass that has better uses away from those to use it here, essentially. And again, we'll touch on this a bit more. And the other big takeaway was that the technology is still very much in a developmental stage. It's not fully commercialized. It's not a mature technology necessarily at this point in time. So, Biomaster hydrogen process. This is a basic sort of process block diagram of the stages for producing hydrogen, and I'll take you through each one, give you a little bit more detail. So first off, we've got the feedstock preparation. Typically, this includes as a minimum some degree of shredding to get down to an acceptable particle size, metal separation, so often done with magnetic separators or eddy current separators for non-ferrous metals. Inert separation, removing any stone, glass, ceramics that could be in there, and then drying. Depending on the biomass source, you could have quite a high moisture content, or potentially you could have a drier source. And one of the key messages on the feedstock preparation is the cheaper you go on the feedstock that you bring in, it might look economical at first, but it's going to lead to an increased level of contamination in your feedstock, which will lead to an increased complexity on your preparation, which is then an increased risk to your process and potentially an increased cost. So things like wood pellets will be far easier to process than, say, municipal solid waste. Moving on to the gasification. So this is the core technology. So there's a few different types, fluidized beds, entrained flow fixed beds. The study mainly focused on fluidized bed technology. And essentially in your gasifier, you're taking your feedstock, sorry, I'll just get the pointer up, your feedstock hydrocarbons, whether it's from wood pellets or municipal waste or wood chips or what have you, exposing it to oxygen and steam at temperatures in the range of 700 to 800 degrees Celsius, and then oxycombusting to gasify it to a syngas, where you're trying to optimize the concentrations of carbon monoxide and hydrogen in that syngas. From your gasifier, you then move through into the treatment of your syngas. So there's various options that you might apply to essentially help remove contamination. So you could have cyclones for removing entrained particulates and droplets, scrubbing to remove tars and ammonia, activated carbon beds for removing metals, and so on. I won't go through all of them there. But again, this ties back into that original message on the feedstock preparation, that if you go with a cheaper feedstock, you're going to have an increased level of contamination coming through your process, and that's going to lead to an increased complexity in your treatment to remove these contaminants, and then an increased risk to your project just due to the complexity and more stuff to go wrong, more things to remove, etc. So your treated syngas then moves forward into a water gas shift reactor. And here the carbon monoxide and the steam are shifted, so you produce your carbon dioxide and hydrogen. And there's two forms of this water gas shift reaction. You have a low temperature version, which uses a cobalt molybdenum catalyst at around 200 degrees, and you have a high temperature, which is operating around 500 degrees Celsius and uses a chromium or copper promoted iron oxide catalyst. The CO2 that is produced in the water gas shift is removed using a solvent-based process, and it produces a very concentrated stream, typically over 90% CO2, which is therefore very optimal for capture and sequestration or utilization potentially as well. So it's very advantageous for capturing the CO2. The final block of the process is the purification of your hydrogen from your gas shifted syngas. This is typically done using pressure swing adsorption, and then followed by further purification steps as may be required to meet your end use for the hydrogen. This is where potentially other technologies such as electrolysis might have an advantage on being able to produce a purer hydrogen without further processing. But there are industries where it's still very much applicable to use the hydrogen from the pressure swing adsorption. Things like steel production will probably be a good target for this technology. So currently, there's a few companies that are operating in this area, looking at converting biomass and biomass-derived fuels into hydrogen. One of these is a company called Q Technology. They use a feedstock of densified refuse-derived fuel, and their gasifiers fluidized bed, and they're targeting producing hydrogen, but they're also interested in producing electricity and liquid fuels. In the course of the study, their current sort of development status was assessed, and currently they're sitting around a technology readiness level of a 6. So it's sort of proven in a relatively similar environment, but the whole process overall has not been proven at a commercial scale and environment. Then another developer looking at biomass to hydrogen is a Powerhouse Energy Group. Their feedstock is made up from refuse-derived fuel as well, but also solid recovered fuels and mixed plastics. They use a different type of gasifier, a rotary kiln, and their product focus is hydrogen, but also electricity. Similarly, their development stage, again, is they're not fully commercialized yet. It's not proven at that level yet, and they were assessed to be at a technology readiness level of 6 as well. I believe there are some other developers in this space, but these were the main ones identified in the study for hydrogen. There were a number of other developers identified in regards to producing the other fuels and methane, methanol, etc. Currently, in terms of the study, we looked at higher capacity plants in the hundreds of thousands of tons per day of feedstock, up to 1 million tons per annum, sorry. And currently, the study found that the largest hydrogen example was processing about 5,800 tons per annum. So it was about 6% of the scale of the small plant we investigated, or we modeled rather. So there's quite a way to go yet to be to a full commercial output. So what are the opportunities for Biomaster hydrogen advanced gasification? So there's only a couple, but they're very high quality, high value opportunities. So the first is the production of low carbon hydrogen. I won't go around that too much. We've had 2 presentations that have talked very well on this and its potential. And then the other is that it's a potentially carbon negative, well, it is a carbon negative technology, and one of only a handful. The others being things like reforestation, land use changes, direct air capture, and carbon capture from bioenergy and energy from waste. So it's one of only a few. So there's some real potential on that front. But there are a number of barriers to developing these technologies and commercializing them. So the first is a supply of sustainable biomass. This really depends on what we found is depends on who you ask as to how much there is. And the truth is that there is a limited supply. You don't want to be taking biomass away from other better uses. You don't want to be affecting food supplies by growing biomass specifically to put in an AGT, for example. So the solution to this is really to keep a reasonable expectation of what the potential supply of sustainable biomass is to use, and then keep that in mind when assessing the deployment scale to use the technology at. The conversion efficiency is also a sticking point. So for hydrogen, the energy and the mass conversion efficiency is quite low because the carbon in your feedstock doesn't end up in your end product. So you're not getting value from it. But the solution there is if you can generate revenue from the carbon dioxide, then that would outweigh that problem because you would be making revenue from the carbon. Product purity, as I said previously, electrolysis might have an advantage here. The purity of the hydrogen is maybe not as high and might not be suitable for all applications, especially where a very high purity is required, such as fuel cells, without a lot of further upgrading equipment. But the solution here is to target those uses that maybe don't need as high a purity, like the steel production, where you could use it without doing further upgrading. A point that was made in the previous presentations is that currently there is no certification or regulation to accredit low carbon hydrogen, and without that it's going to be difficult to generate additional revenue for it being low carbon, which is required to make the process viable. But again, the solution here is actually being worked on. You know, the hydrogen economies is something that's being really pushed from a lot of places to achieve net zero. So it seems likely that this will be resolved in the near future. Value of the CO2, there's currently not the transport and storage infrastructure or the financial incentives in place to push for revenue and to capture that CO2. And really for this process that's needed. The solution here, again, is already in development. The mechanisms are being pushed for the net zero and all these sort of projects to capture carbon. So it seems very likely that these will be overcome in the near future, which will aid the AGTs. Availability of technology. So all the existing examples of the technology at the moment are at typically smaller scale. Some of them had quite a limited track record of operation. Now the solution to this is probably improving the economics. If there's more of a value in this technology, then more money will be invested in the R&D and development, and it's likely that those operational issues will be overcome with enough time and effort. And it's also true that of the AGT technology studied, the hydrogen production as opposed to the liquid fuels was arguably the simplest process, so technically more feasible. And lastly, economics. Okay, this kind of goes back to those previous points that you really need value from the CO2 that you could capture as well in order to make this economical. And this feeds into the techno-economic analysis that we performed. And we produced this plot here that demonstrates the levelized cost of the hydrogen produced both from waste to hydrogen and from biomass to hydrogen. So looking at this from left to right, you've got a small scale waste plant, a large scale waste, small scale biomass, large scale biomass, and on the right hand side here you have 3 counterfactuals. So we've got steam methane reforming with carbon capture and storage, and then electrolysis here. So you can see quite clearly that the AGT can't compete on price with the SMR, even with carbon capture and storage. If you start this was a study calculated the levelized cost without taking credit for a value of the carbon dioxide captured. So if you start putting that in, obviously this will change. But then if you're crediting carbon dioxide on the AGT, you have to credit it on the SMR with carbon capture and storage. So it's still not going to be competitive on that front. However, with electrolysis, you can see there is some benefit there. They're in the same sort of range. There is some potential in that line by comparison there. Another interesting point is that with the current spike in gas prices that have gone up quite astronomically in the UK, that could well push the SMR benchmark here up towards the £5 per kilo mark, which would actually bring it far more close to being competitive if the prices were to stay at that level. So does this technology have potential to be part of the future energy system? The answer to that is yes, it does have some potential. Is it going to solve all our problems? No. It's sustainable feedstock supply is limited, and it has a lot of other uses. So it's never going to be able to fill the full market to provide all the hydrogen we could possibly need or want to achieve net zero. What is the technology for? So this is an interesting point, that there's really 2 main products of this process. It's your low carbon hydrogen, but then there's also your CO2 capture from atmosphere, because it's a negative emissions technology. So which one of these 2 would actually end up being the main revenue of the process? And that's not really clear at the moment until the hydrogen and the CO2 economies are really established. We're probably not going to know that answer. So in 5 years' time, this presentation, instead of biomass to hydrogen, could well be biomass to CO2 capture. So it's an interesting point, and we'll see what happens in the future. And that's all from me. Thanks very much.
Okay, thanks, Stephen. We'll remember that, make a date for 5 years' time.
Yeah.
I'm actually going to ask you a question to estimate what the uplift might be, actually, depending on the carbon price, because I don't think you quoted that. But anyway, think about that during the coffee break. So we are running over. I'm sorry about this, but very interesting presentations. So we're going to have the last presentation and then take the break, and that's from Jane Durling at the Environment Agency, who's going to talk about the best available techniques for blue hydrogen production with carbon capture and storage. So Jane, if I can pass over to you.
Thanks, John. Thanks for inviting me to talk about best available techniques for blue hydrogen production with carbon capture and storage. I'm a senior advisor in the energy team in the environment and business part of the Environment Agency. I just noticed I've got the wrong date on there, so apologies for that. Next slide, please. So I'll be talking about the batch review that we've done and the guidance on best available techniques over the last year. We are due to publish those. They're not quite ready to do so, but the batch review is available on request. So in terms of the details of what we're going to talk about, what is BAT? What is BAT guidance? Just a quick look at the technologies we've looked at, and then key points for guidance, next steps, and what we've published. Look briefly at BAT and the UK hydrogen strategy and future guidance we're going to hopefully publish in the future. Next slide, please. So what are BAT, best available techniques? BAT are defined in the Industrial Emissions Directive, which is currently the basis of our regulation of industrial processes in the UK, although it's an EU directive. They are the most effective and advanced stage in the development of activities and their methods of operation. They have to be economically and technically viable, and they provide the basis for emission limit values and the permit conditions. We need to prevent, and where that's not practicable, reduce emissions and the impact on the environment as a whole. And the full definition can be found in the directive linked there. Next slide, please. So when is BAT guidance needed? So BAT reference documents, or BREFs, which were previously produced and will still be being produced by the EU's civil process, have conclusions and set BAT associated emission levels and descriptive BAT standards. No BAT reference document covers hydrogen from methane with carbon capture and storage explicitly, and these are considered as emerging techniques, although there are some references to similar processes in ammonia production and the refineries BREFs. Article 14.6 of the directive requires the regulator, after prior consultations with the operator, to set emission limit values and other permit conditions on the basis of its own determination of BAT, which has to give special consideration to the criteria in Annex 3 of the Industrial Emissions Directive. The permit conditions must protect the environment and prevent harm, and they cover the basic obligations of the operator, as well as any environmental quality standards which require the operator to go beyond BAT in order to meet the standard. For example, we have air quality standards in the UK. We must encourage emerging techniques, whether or not these have been identified in a BAT reference document. Next slide, please. So these are the criteria in the annex I mentioned before that need to be considered when we're using the Article 14.6. So I'll just leave you to read those through, but they're the typical things you'd expect in terms of environmental permit, looking at emissions, looking at minimizing waste, reducing use of hazardous substances, key topic here, energy efficiency, raw material, water usage, preventing overall impact. In terms of accidents, these plants are also likely to be COMA or control of major accident hazard establishments, which we would jointly regulate with the Health and Safety Executive. And we also take account of published information, which it could be international information on techniques. Next slide, please. So what's the development process for BAT guidance? A BAT review informs BAT guidance. It summarises the available evidence, both published and direct from technology providers and operators. and it identifies the key aspects which will influence the environmental performance and any best practice identified. It's been developed via an iterative process by the contractor Costain and the Environment Agency in consultation with interested parties in industry and agreed by NRW, SEPA and NIEA, who are the other UK regulators, environmental regulators, as part of a technical working group. It will and has already been able to assist applicants to apply for permits and regulators to assess permit applications, but must allow a range of techniques and performance for emerging techniques. It doesn't set back standards or limits at this stage, but it will help to identify where evidence is required to enable standards to be set. Data can be obtained under the permit during commissioning and operation of the plant. Pre-operational conditions can also be set. To note, under the environmental permitting regulations, hydrogen production is an inorganic chemicals activity, and as production of hydrogen as a gas, and carbon capture and storage is also an activity, although we would only permit up to the boundary of the installation, not transport and storage. So we're permitting around a boundary, within a boundary, which we call an installation. Next slide, please. So these are the technologies that were identified as being relevant at the moment for the BAT review and BAT guidance, some of which have been talked about indirectly already. Steam methane reforming, which is the current main process, autothermal reforming, gas heated reforming with some combinations available, or partial oxidation. And all of these will of course need carbon capture and storage, use of methane or refinery fuel gas, being the main, one of the main inputs. So next slide, please. I'm not going to talk in detail about those because there's not enough time really. So this is just a summary of the inputs and outputs which are common to all of these processes, and the types of unit operation dependent on the details of the technology. We're interested in the most appropriate techniques for each process or unit operation, which will be proposed within this box, so that we can look at the environmental performance of the techniques or combination of those as a whole. This project's enabled an in-depth review of these proposed techniques based on information provided mainly by technology providers. It was clear that the key areas to consider would be energy efficiency and integration, CO2 capture efficiency, raw material efficiency, any abatement required, and all aspects of emissions to the environment. Next slide, please. So just quickly going through the key points that we'll be putting in the guidance, and it's already expressed in a section of the BAT review document. So overall capture efficiency is obviously key, as has already been mentioned. We're expecting, and the operators and equipment manufacturers have agreed, that more than 95% is certainly achievable, and we'll be pushing that upwards where we can. It's typically, as previously been said, by absorption in the solvent with regeneration, balancing between delivering carbon dioxide at high pressure to storage, but that's limited by avoiding high temperatures, which would potentially degrade the solvent more quickly, in this case usually amine solvents. The feed gas energy conversion will impact on the total CO2 captured from the process, and the capture rate should be near complete for in-process carbon dioxide capture, and we'd expect more than 95% capture for post-combustion capture where needed in these processes. Carbon in the tail gas, this should be minimised by optimising conversion, and may need post-combustion capture on a small scale. Capture efficiency will vary depending on the operating regime. For example, we need to manage, they need to manage if swing production is needed in initial phases of the operation due to availability of users. So obviously, if you've got, not a steady sink for your hydrogen, your plant's going to be going up and down a bit, which isn't ideal for the capture efficiency. Next slide, please. So for energy efficiency, obviously, it's a key part of this. Energy balance is dependent on the technology choice. It defines the electrical power requirement, whether there's any excess high pressure steam to power any drives or low pressure steam demand, and also the power demand of any oxygen supply. So currently the carbon footprint of the external electricity supply is not in scope of the installation's permit assessments. So we don't look at life cycle and the source of the electrical power. It could be integrated with cogeneration to improve electrical efficiency, operational flexibility, and potential for higher. There is a potential for higher thermal efficiency there. In terms of water supply and quality, this is going to be key not only for the hydrogen with carbon capture and storage, but also for any green hydrogen or hydrogen via electrolysis. So water supply, we really got to involve the UK Environment Agency's water resources teams in assessments for all types of hydrogen supply. Feed gas quality will determine desulfurization and pre-reforming processes needed to remove contaminants, especially sulfur, to avoid catalyst poisoning, which minimizes waste if you can minimize your catalyst poisoning. Pre-reforming to convert heavier hydrocarbons and some methane to carbon monoxide and hydrogen. In terms of your hydrogen product, there will be a specification, so you may need to consider inerts removal. Any carbon in product streams will need to be accounted for at some point, yet to be determined. So you can't really just sort of sell your carbon through your hydrogen stream, or maybe you can if that's acceptable downstream. But we won't assess that necessarily, or come on to that later. In terms of carbon dioxide specification, that will be defined depending on where it's going to be put. CO2 compression delivery pressure will depend on whether the CO2 is to be transported in the gaseous or dense phase. And this will be a significant energy user to get the CO2 to the right pressure. Next slide, please. Okay, so where these processes may need post-combustion capture, then particularly the steam methane reforming process, where you've got a large gas heated reformer, which is like a big furnace, you will need post-combustion capture of some form there if that's the process you're using. Solvent selection is critical. There's a balance between the energy requirement, which tends to be reduced by more complex amines if you're using an amine solvent, but the more complex amines have more potential to form hazardous degradation products within the solvent system, which may result in emissions to air. There's also the potential for post-emissions formation of nitrous amines and other degradation products in the atmosphere once it's been emitted. So solvents need to be tested and the performance proven. Next slide, please. So in terms of emissions to air, again, these are sort of more standard things we'd be looking at. So fired heaters, steam boilers. There's potential for higher levels of NOx formation where you're burning hydrogen, perhaps, and therefore you may need to abate the NOx. Flare emissions, there shouldn't be routine flare emissions, and you may need to model the emission to demonstrate that there's no significant impact at ground level. And the carbon dioxide vent, there'll be some loss of CO2 potentially, and also loss of solvent or degradation products. So basically, you'll always need to do air dispersion modelling for these complex permits. Okay, thank you. That's the next slide, please. Emissions to water, again, they're likely to be continuous effluent treatment discharges. So all those sort of usual aspects should be looked at for a large plant, which are just listed there. I won't go into any particular detail, but really water treatment and reuse should be maximised. There is potential for ammonia, amine compounds, etc. in waste streams, which need to be dealt with. Next slide, please. Again, just very briefly, waste streams, they'll, for a large production plant, there'll be typical liquids and solids from all the materials that you're using within that process. So all of those need to be minimized, and there's some examples there. Next slide, please. Monitoring is obviously important for us to understand the performance of the plant on a short term, and on the basis of finding out information more about these processes, which are considered emerging techniques. So there'll be an intense period of monitoring, certainly during commissioning, I'm sure we'll require that, and then ongoing once the plant is up and running at a more steady state, to do continuous monitoring where appropriate on all emissions. And that includes CO2 capture performance, obviously, and the key process parameters such as energy efficiency and solvent performance. Next slide, please. So what's the next steps on our batch review? Well, it's complete. It's available on request. Just developing that and getting that into the format to put on our government website, .gov.uk. And I keep putting a date on here, but it keeps going back. So I'm expecting it to be early next year at the moment. The batch review will be referenced in that guidance document, and the batch review will be published on the UK CCSRC website, I hope, which is very kind of John and colleagues to put it on there. It's also where our current batch guidance is as well, for post-combustion carbon capture. Next slide, please. So these are our current published guidance on post-combustion carbon capture. The link is there, and we've also got one on, that's also the batch review. So the guidance and the review link there. And there are also some webinars that we've done previously on myself and my colleague John Henderson talking about this for the IMechE. If you're a member of the IMechE, you could access those. Next slide, please. So future back guidance. We're just commissioning a project on hydrogen production by electrolysis in a similar way to do the same sort of thing for that. And ongoing work to support post-combustion carbon capture and storage. You can read the projects there. Obviously, we're concerned about amine emissions and degradation product emissions. So we need to develop environmental assessment levels for those. Next slide, please. So this is the hydrogen strategy. UK's hydrogen strategy has been published. The consultation on that's on the low carbon hydrogen standard is now closed. So there is a strong link there, potentially a strong link there. We can help in terms of monitoring and reporting and verification aspects of the low carbon hydrogen standard against actual operator performance for these type of plants, and also for the hydrogen bioelectrolysis plant when they get going. So we're liaising with BEIS, the government department who are leading on this, and they're also funding some of the work. Next slide, please. Thanks very much. Sorry, it's a quick whiz through, John.
Oh, that's okay. It's very interesting.